Hey guys, welcome back. So today we're going to be talking about how to compute the domain and the rules that fall behind it. So let's get started. So with domain, all we care about is a set of inputs of the x. We just care about the x. We never even think about the y. So whenever we're computing this, we need to ask ourselves which values of x are not allowed. So first we look at the function that we're dealing with, we identify the function that we're dealing with, and then we ask ourselves what restrictions does that function have. So the first type of function that we're going to be dealing with is going to be polynomials. So let's talk a little bit about polynomials, right? So polynomials do or do not have restrictions to the domain. So the answer here is going to be that polynomials do not have restrictions to the domain. The reason why is because polynomials, they increase infinitely to the left and they increase infinitely to the right. So just because the polynomials do not have restrictions to the domain, that does not speak for the range. Just because you can input everything into the domain, you can input any x into the domain, so you can have infinite amount of inputs, that does not mean that you're going to have infinite amount of outputs. Alright? So what we have here is that range, and I'm going to try to write as neat as possible, because I'm really not very good at this. Range does have restrictions. So when it comes to polynomials, don't assume just because the domain doesn't have a restriction that the range does not have a restriction. Alright? So now let's look at an example here where we're given f of x equal to x squared minus 1. So here we're given a quadratic function with an even power, and so the first thing we do, like I said, is just we first look at the function. Okay, this f of x equal to x squared minus 1. Then we ask ourselves, what type of function is this? Okay, this is a polynomial. Now, after that, we ask ourselves, what restrictions do polynomials have? We don't have any. So actually, the answer is going to be all real numbers, because all numbers go, right? So, since the answer for this is all real numbers, we're going to use two different types of notation to express this all real numbers answer, right? This answer for a domain. We're going to start off with interval notation, right? And the way to express all real numbers in interval notation is negative infinity to infinity, which means you can go infinitely to the left, infinitely to the negative side, and infinitely to the right to the positive side. That's all that really means, and you have no restrictions. So the next type that we're going to be covering is going to be set builder notation. Set builder notation. So with set builder, it's actually like really hard to draw this thing, and we're going to have a little fancy parentheses. It's supposed to look a little different, but maybe you guys are a little better at this than I am. I should draw it again. Looks a little better there, right? It's going to open up with a fancy little parentheses, and then we're going to have x, a vertical line. That means x exists where x is a real number. So the fancy little r there with the two bars means all real numbers, right? So now we have seen how to do this in interval notation and in set builder notation. So now let's look at another example, example B, which is only different from example A because it has odd powers compared to example A, who has even powers. Alright, so once again, it's the same procedure. We just look at the function f of x equal to x to the 5th minus 4x cubed plus 2. Okay, what type of function is this? It's a polynomial. And then we ask ourselves, what are the restrictions of polynomials? They don't have any, right? So once again, we give our two notations, our interval notation, which is from negative infinity to infinity, which says we have all real numbers are good to go, and our set builder notation, which is x exists anywhere that x is a real number. So that's all we care about, that's all we have, and then we're done with polynomials. So now we're going to look into radicals, right? We're going to look into, whenever we have a radical, we identify a radical, we look at the restrictions of the radical, right? And how we're going to compute the domain. So here we have that the inside of the radical, radicand, which is the fancy way of calling it, right? Your professor may say like, oh, you know, like when we look at radicals, just focus on the radicand. That's just a fancy way of saying the inside of the radical. Just say the inside, right? So when we talk about the radicand, there's some rules about the radicand, right? The radicand has to be negative, positive, or 0. Okay? So we've always been told that the inside of a radical has to be, actually, we're more told that the inside of the radical can't be negative, right? So what we know is that it just cannot be negative. So if it can't be negative, it means that it can be positive, and it can also be 0. Alright? However, this, when you're told the inside of a radical must be positive or 0, is very, very general, and it gives room for mistake. Because actually, this is only true for even power radicals. For square roots, fourth roots, sixth roots, in that sense. Right? Whenever we have a cube root or a fifth root, this does not apply. So this only applies when we have even roots, such as square root of x, fourth root of x, and so forth. That only applies for those radicals. Alright? So now I'm going to give you two examples, example A and example B again, of how this can be applied. So the first thing we look out for is it an even or is it an odd type of root? Okay, this is a radical, so we know there's a hidden 2. There's a hidden 2 there that no one ever talks about, but we all know it's there. There's a hidden 2 there in front of a radical. So it's an even radical. So then what we're going to do is we're going to make sure that the inside of the radical, the radicand, is only positive or 0. So what we're going to do here is that we're going to say that we get the inside of the radical, which is x minus 1. Okay, and to find out where it's true, we set a greater than or equal to 0. Because that greater than 0 means that it's positive, and equal to 0 means that it can be 0. So this is every scenario where it's not negative. Not negative, right? So whenever we have a radical, in short terms, we just set the inside of the radical greater than or equal to 0. But that's the reason why. Because it cannot be negative. And it could be positive, or it could be 0. So now we solve for x. So just move over this 1. So x greater than or equal to 1. So in this case, the easier notation to jump into is going to be our cell builder notation. And you'll see why. Because we're just going to do something like this. We're going to put our big bracket. Right? And then we're going to put x exists such that x is greater than or equal to 1. So how this problem is solved, cell builder notation goes a little easier, but we can always write it in interval notation. We can always go back and forth. So I'm actually going to do I'm going to draw the solution, this answer. I'm going to draw it in a number line. So I'm going to do a number line here in green, where I put 0 in the middle, and I put the factor 1, right? And now I'm going to have everything greater or equal to 1. So everything to the right of 1, right? So I'm going to have shaded in dot, and now we're going to go to the right of 1. Alright? So if you guys forget which way to go with inequalities, because it happens to me all the time, all we're going to do is we're going to draw an arrow on the inequality. So you see how we have an arrow now facing to the right. So that's how we draw our inequality. We have an inequality to the right. So since we have everything from 1 to the right of 1, that in interval notation is easier to read, and it's going to tell us that we're going to go from 1 to infinity. Now, when it comes to notation, in interval notation, the parentheses of the brackets are key. So when do we use a parentheses and when do we use a bracket? We use a parentheses when the number is not included, or when it's infinity, because infinity is not a finite number, so it cannot be included. So infinity always takes a parentheses, right? So here we have an infinity, so this infinity here is going to take a parentheses, and now we ask ourselves, is this 1, is it included? Alright, so yes, it is greater than or equal to 1, so the 1 is included, so the 1 gets a bracket. So our notation is going to be from 1 to infinity for a domain of this radical. Now, we go into example B, where we look at the radical, and we first start with radicals by asking ourselves, is it an even radical or is this an odd radical? So we look at it, we spotted the 3, so this tells us it's an odd radical. So we haven't talked about the rules for odd radicals, right? But actually the reason why we haven't talked about them is because there are no rules for odd radicals. Odd radicals are just like polynomials, so we're going to put that here. Odd roots or odd radicals are just like polynomials. It means that they have no restrictions, right? So they have no, let's put that in a different color, no restriction, right? They travel infinitely to the left and infinitely to the right. So now, how to write the domain of a function that has no restrictions? That's going to be from negative infinity to infinity, or if we do cell-builder notation, we're going to have x such that x is a real number. And that's a very bad parentheses. Let's redraw that again. Still bad. Let's give it another shot. Probably just going to give up soon. There we go. That looks a little better. Alright? So that finishes off our radical functions between even radicals and odd radicals. So now we're going to talk about rational functions. This is our third type of function we're going to discuss here, and how to compute their domain. So whenever we talk about rational functions, all we care about is the numerator or denominator. What is it that we care about, right? And it cannot be 0. So when we say that when we have rational functions, what can be 0? The top of the function or the bottom of the function? And that's going to be the bottom of the function. So therefore it is the denominator. The denominator cannot be 0. Because whenever the denominator is 0, we say the fraction is undefined. So now this sentence is kind of like caveman. Denominator cannot equal 0. Fraction undefined. You know, but it's exactly the point of it, right? So whenever the denominator is 0, the fraction is undefined. Or we can read it as the denominator cannot be 0, so the function is not undefined. So the fraction is not undefined. Alright? Or the function. So let's look at the first example, example A. So when we look at this example, all we care about is the denominator of this function, right? So when we have 5 over x minus 2, all we do is get the denominator, right? And it cannot equal to 0, so we say u cannot equal to 0. So then we solve for x. So we solve for x, and then it gives us x cannot equal to 2. So the bottom cannot equal to 0, which is x minus 2 not equal to 0, then x not equal to 2. Why is that, right? So if I plug in 2 into my fraction, right? If I plug in 2 into my fraction, I'm going to have that 2 minus 2 is 0, and I cannot have a 0 in the bottom. So that is exactly why. But if I plug in anything else, like if I plug in 1, I get like 1 minus 2, so I get a negative number. That's okay. This is not a radical, an even radical. It's just a fraction. We can have negative numbers. So now we go into the more natural notation, and in this case, the more natural notation is going to be cell-builder notation. So it's going to say that x exists anywhere that x is not equal to 2. I guess the second parenthesis is always a little harder for me to draw. So what we're saying is that we have no restrictions here in the domain except for when x is equal to 2. So when x is equal to 2, we have a problem, and we're going to say that this right here is no good when x is equal to 2. Alright? So now we're going to go again, we're going to translate from here to interval notation. So I'm going to draw again a number line, just so you guys can see it. I'm a very visual learner, and I hope you guys are too. And this is the easiest way to go from cell-builder notation to interval notation. All right. So we're gonna say that it's everywhere but 2. So actually, I'm gonna delete that circle, and I'm gonna open circle here, and it's everywhere. It exists at every x but at 2. Right. So it's a giant hole at 2. All right. So what this means is that I'm actually going to go from negative infinity. I'm going to exist from negative infinity to 2. I cannot include 2 because it's not there, right? So I'm going to write that in there. Negative infinity to 2, right? I cannot include 2, so I'm going to have a parentheses. Is that included? I'm going to have a union to show that I have a little gap there. I'll have a little hole there in my domain. And then I'm going to go from 2 again, not included, all the way to infinity. Alright, so you write that in a normal line. You write negative infinity to 2 with parentheses, then you write a union, and then you write parentheses 2 to infinity. And that is how we successfully write the domain of a rational function with its continuity on the denominator of 2. Alright, so now we're going to look at example B, where we have 1 over x squared plus 1. Alright, so the same thing. We look at the function, we ask ourselves, what function is this? Is a rational function? What are the restraints of a rational function, the restrictions of a rational function, and is at the bottom cannot equal to 0. So I'm just going to do just that. Okay? So, now I'm going to have x squared plus 1 not equal to 0. So once again, I'm going to solve for x. I'm going to be lazy and just move over this negative 1. And then take a radical of both sides. Right? But since I'm taking a radical, like we said, radicals cannot be negative, right? So whenever we have square root of negative 1, we don't have any real solutions, right? So we have no real solutions, which that's going to translate to, we have no real solutions. But what that means for us now when we care about domain is that we have no restrictions. So in this case, no real solutions turns into no real restrictions. So now it's going to tell us that our domain for this graph, for this function, is going to be negative infinity to infinity. Or we have it in sub-Boolean notation, it's going to be x exists such that x is a real number. So that's all we care about, right? We all care about the denominator. We don't even look at the top. We just boom, we get it done, and we're done. So that's how we do rational functions, right? So now we're going to deal with the other section of these functions, which is when we have multiple functions put together. Not just a rational function, not just a radical function, not just a polynomial. We're going to have different functions put together, right? So we're going to see how that is going to be a little trickier, but there's a very simple way of following the rules that can give you the answer. So let's get started. I'm going to remove myself from here. Actually, I don't need to because we're doing example A. So for letter A, we first have to cover the learning here where it says we must find the blank, which here has to be a union or intersection of the domains when dealing with multiple functions. So what I'm saying here is that we're going to have different functions, right? We're going to have several functions, different types of functions in these examples, right? And then we have to deal with the domains of their individual functions because every function has a domain of its own. So they all kind of have like an opinion, right? So I'm a function, I have my opinion, and you have your opinion. We have to come to an agreement where we both agree on the answer, whatever we're doing, right? So in this case, our agreement is the intersection. Our agreement is going to be the intersection between you and I. So let's say you're function A and function B. Our agreement is going to be the intersection of us, which is going to be the domain for both of us, right? So our agreement is going to be the domain that is the intersection between our opinions. So now here we look at the top and we look at the bottom, right? So before when I taught you rational functions, I just kind of told you to ignore the top, right? So now that you have learned rational functions, that you have learned radical functions, and now that you have learned polynomials, we're going to look at everything. We look at the top and we look at the bottom. Because you never know where you can find a restriction that you need to play with. So the rational functions that I gave you didn't have restrictions, but these rational functions may. So let's look at the top. Okay, so let's write this like this, right? So top is going to be x minus 2, and it's a polynomial. Just write poly. Let's not be lazy and write nomial. So this thing doesn't have any restrictions, so I guess we don't care about it. So no restrictions. So we're kind of done with the top. Now, let's look at the bottom. Let's look at the bottom. Okay, the bottom is square root of x plus 1. It's a radical function. Let's write that in blue so we can be consistent in our color. Square root of x plus 1. It's a radical. And not just a radical, it's an even radical, which is the ones that actually have restrictions, because the odd radicals don't have restrictions, right? So the even radical, what we do with them, like we said, it was just whenever we have a radical, we set the inside the radicand greater than or equal to 0. So we're going to do just that in green. X plus 1 greater than or equal to 0, right? So we're going to solve for x, and it gives us x greater than or equal to negative 1. So now we have our restrictions covered for the bottom. So now what we're going to do here is something I like to do when we have multiple domains. We're going to draw number lines, and then we're going to see where they're all going to match, right? So I'm going to draw, I rarely use the color black, but I think in this case it's not black. So that's black. But I'm actually going to use it in this case. So this is going to deal for the top. This is going to deal for the bottom. And let's put like D for the overall domain. So the T is going to deal with the domain of the top, the B is going to deal with the domain of the bottom, and the D is going to deal with the domain of the whole thing. So like we said, for the top, we had no restrictions, so we're just going to have a full number line. And we're going to connect these number lines by 0, so we kind of have a reference point. And then when we have our domain here of the bottom, it was everything greater than negative 1. So we're going to go to negative 1, and we're going to go everywhere greater than or to the right of negative 1. It's going to be okay. So that takes care of the domain of the top and the domain of the bottom. So now what we're going to do here is we're going to kind of like squish these two number lines together, right? We're going to bring top number line with the bottom, and we're going to see where they both have shading, right? So the only problem, the top domain doesn't have any restrictions, but the bottom domain does have restrictions, right? So we look at where it's kind of like white. It's kind of like, it's empty here for the bottom domain, right? So we cannot include this piece right here at the top, because they both need to agree that they both have that, right? So think about this intersection of domains, like your friend going out to dinner and I'm going out to dinner. You and your friend are going out to dinner, and then you guys want to pick a restaurant, right? So my budget, let's say your budget is T. So you have a lot of money. So you have all the money that you can have. But your friend doesn't have all that money. So he has less money than you do. So where can you go? You can go where your friend can go, unless you're willing to pay for him, because you have to go where the one with the less money has. So in this case, the one you have to cover his restriction. His restriction in this case is having less money than you do, so you need to cover that, right? So in this case, the domain of the whole function can't be the one of the top with no restrictions, because the bottom has a restriction. So you got to be considerate of the bottom function and cover its restriction, right? So where they both meet, you're going to go limited by the bottom's domain, right? So you look over here, and then these guys you can't count them. So your domain has to start here at negative 1. And then you look to the right of negative 1. Does the top have any restrictions after negative 1? No, the top does not have any restrictions here. There's no restrictions, there's no holes, there's no little gaps anywhere we got to talk about. So, and how about the bottom? The bottom doesn't have any restrictions, any gaps, or any holes that we got to talk about. So, then our total domain is going to be from negative 1 to infinity. Alright? So we can write that in interval notation as negative 1 to infinity, right? Or we can write it in cell builder notation as x exists such that x is greater than or equal to negative 1. So there are two ways to write our notation for this domain, and it's just very important to understand that you need to be very considerate of where both functions intersect, right? So you look at for your restrictions and your friend's restrictions, all right? So Now let's move on to example B. Is that going to be any different? The only difference if we look at example B is the top now it has a radical function, and the top now has a restriction. So we got to look out for the restrictions to the top. So we start by writing the top, right? We identify the function, how we always do this first. Identify the function. It is radical. Let's write it in blue to be consistent. 2 minus x. Top, right? This is radical of 2 minus x. And this is a radical. It's a radical function. And it's an even, so we care about it, right? It's an even function, so we care about the fact that it has a restriction. So we compute the domain of the bottom, right? So we do 2 minus x, so it's in green. I'm trying to be as consistent as you guys can so you guys can follow. 2 minus x, right, greater than or equal to 0. Now we're going to move over the 2, so we have negative x greater than or equal to negative 2. And now, here's the only difference between when you solve an equation with an equal sign or when you solve an equation with an inequality sign, right? Now that you have a negative x greater than or equal to negative 2, you're going to have to get rid of that negative, so you're going to have to divide by a negative 1, right? So when you divide by a negative in inequality, just a quick reminder, you have to flip the inequality. So if it's going this way, if it's going like face like this, now we're going to go, boom, the other way. Okay? So now we're going to divide by a negative 1 on both sides. So we actually should put like a little red here, like I'm multiplying by negative 1. I'm multiplying by negative 1. So now it's going to flip, and it's going to become positive 2. Right? So now we have that our only restriction for a radical is that the x values that you can input has to be less than negative 2, right? So have you guys thought about what happens? I just told you this is the restriction. It has to be this, like this greater than this, bigger than this. So what happens if you don't input something in that domain, something in that interval, right? So anything instead of being less than 2, something greater than 2, right? So let's say we input 3, which is not in that interval, right? So if I input 3 into radical 2 minus x, that'd be radical of 2 minus 3. So what is 2 minus 3? That's negative 1. So radical of negative 1 is going to be a negative number. So that's a non-real solution. So it does not work if you fall outside of the interval, right? So let's go back to the whole dinner idea, right? So let's say your budget is less than $2, right? So you can only check out the dollar menu and maybe get like a cookie or something. So if you go and try to buy like a whole Happy Meal, it's like $4 or $5. I don't know how much it is right now. The bank is going to say you're denied. So the same idea. You cannot input 3 into my function, and you cannot buy the Happy Meal because you don't have enough funds. You only have $2, and then you can only use that much. So that is your restriction. So it's a real life application of applying restrictions and the actual domain. All right. So now let's deal with the bottom. Which is a x minus 5, which is a polynomial. So we like these. We like polynomials. Why do we like polynomials? Because they have no restrictions. Alright, so once again we're going to draw our 3 number lines. Our top number line, boom. Our bottom number line. And then we're going to draw our domain number line. Okay, so now the story changes, right? So now, let's say you are top and your friend is bottom. Unlike like last time, right? So now let's say you're going through some tough times, right? So like I said, you and your friend are trying to go out to dinner. So you have, let's connect these by 0. So let's say you have a budget of $2. Okay, so you can only buy anything that's less than $2. Right? So now, let's say your friend just got paid. So he's happy. He wants to go out. He wants to go drinking. He wants to just spend a lot of money. But you are broke because God knows what you bought. So, let's say your friend has no restrictions. He's a polynomial. He's happy. You're a radical. You're not happy. So a polynomial, he has no restrictions. right? And now you guys have to agree again. So now what happens is that you're like, hey buddy, like, I only got $2. We can't go out to dinner, too expensive. We just gotta, chill out and check out the dollar menu. So your friend is gonna be considerate, and you guys are gonna come to an agreement, which we call the intersection between your argument and his argument. Your argument is I only got $2. His argument is like, I got all the bucks. So where you guys meet, see if you guys are over here, it works for both of us because you guys can both afford this. Which there's no real relevant value of this because this means like a negative number unless you're getting paid to eat. You can have a negative meal. That's weird. So anything below 0 works, right? But then when we check over here, for example, right? Here, only your buddy can eat here. This is your buddy's price range, so you can't eat here. So the intersection of your domain is limited by this 2 right here, and anything to the left of the 2 works. But then anything to the right of the 2 doesn't work because you cannot afford it. You're broke this time. Last time you had money. Alright? So now we're going to write this domain in interval notation, and I'm going to remove myself from here. Boom. So we can talk about this a little better. So now it's everything less than 2, right? So it's actually going to, the leftmost point of this domain is going to be negative infinity, right? Because you're coming from all the way from negative infinity, and then now you're going all the way to 2. So since you're going from negative infinity to 2, you always read domain from left to right. It's going to be not a bracket because we're talking about infinity. We're going to have negative infinity. Infinity always gets a parentheses, and then it's going to go to 2. Now we ask ourselves, is this 2 included? And the answer is yes. Alright? So now we have completed how to find this interval notation. So come back over here, and we're going to talk about how we have successfully found the domain of this 2 different kind of functions. So this is how you found the agreement between you and your buddy. Alright? So then there's going to be a bunch of different practice problems when this thing gets a little tougher, and then I'll see you next time. So look out for the practice problems. Stick around.